Okay, so today I wanted to introduce the Factori. Is the Gig Lab here. This is the smart contract development. It's for the Taser smart contract. So it's a tool that you can use in the Taser smart contract to interacting with the smart contract. When you're using this library, you are able to use the TypeScript language or the OCaml SDK to form any mix and match contract. So I already installed in my computer about the Factori. You can either install it by copying from the Docker and you follow the example, or you can use the OPAM to create the OPAM suite and build and then make. So in this website, they give the example of how you're using TypeScript to interacting with the smart contract by using the keyword, firstly to import the KT1. KT1 is the address of the smart contract into the from the Taser blockchain. So you have the Factori keyword, import, you import KT1, the directory, and the exact address and the type of the programming language that you want to generate it. In this case, is TypeScript, the name and the name of the functions that or you can also import it by using the mications. For this, you can have use Factori, import mication, the directory, the name, and the name of the contract that you wanted to call in your Factori library, and the path to either to JSON or the TZ is the smart contract. It's the extensions for the mication smart contract, and you use TypeScript to indicate the language that you wanted to export. And from there you can install the TypeScript dependency and compile your SDK. And if you have this error, you can use some of the fix that they propose. For the OCaml SDK, for the contract, you can use the starting from the empty project by created the directory using the keyword Factori empty project and the name of your created factory. You go inside this new directory and you do make underscore OPAM and then make tab to build the project. So at TypeScript, you also have two kind of import. Either you know the address, or you can import the mication smart contract, but for the type, you indicate -- OCaml, and sometimes you also have to use -- force to actually forcing these executions. And then you can able to run from you set up the environment again and you build your project. And so this is the general example of how to actually started the Factori and what is it. And here they have a web blog, the blogs of the company called Factori, who is the one created the Factori. You can come here to read more detail about what is it used for, the roadmap, and the same thing with install with more packages and example of when you import the KT1, from more example like the name and the network and the type and force where you can create it. then you can have the small scenario, how to interacting with the smart contract you just imported it. So I will go into this directory. This is the purpose of the tutorial today, is how to rerun or how to follow the example that provide inside the factory example. And this is the general ideas that they're gonna use the OCaml to write in the smart contract, and then using mLIGO to generate it into LIGO language. So LIGO is a top level language that generated to Michelson. So instead of directly having the Michelson smart contract, you can go to several steps and using LIGO, then generate it to Michelson, and then using the factory, you import this smart contract. Either you know the address of the smart contract, or you call directly into the smart contract, and then you have the interface of either the language TypeScript or OCaml. Then you interacting with the Thesis network. So first, let us start it to install the mLIGO. I think I already have. So you're just using opam bint, you pin this, and then you're using eva opam env to set up your environment again. And for that, you also need to write in your Dune file, declare something like the library, the preprocess pps is mligo.ppx. And to be able to start using it, you just use open mligo. And then because we need, now we have the OCaml, we using mligo, then we using LIGO to actually export it into the Michelson. I assume that you already installed LIGO in your computer. This is the website where you can have all the tutorial and how to install and more information of the LIGO. And so now we're using the example called perfect numbers. So this is the smart contract created number validators. So that a user or a smart contract propose a number with a specific property, such that the prime number, perfect number, or Fibonacci number. And if the number that you provide satisfy the property and exceed the current number, then you get the reward with some XTZ. Otherwise, we fail to call the smart contract. So the example I will follow today is exactly what they propose. It's called perfect number. The perfect number is the number which is equal to the sum of its divisions, excluding itself. So you can get more information in the Wikipedia of definition, what is the perfect number. And so what we need to write in our smart contract is that we need to provide the two informations. Firstly, about the type of the storage and the entry point, the main entry point of our functions. And so for the name of this example, let's name the contract is called perfect number.ml. So remember, this is the first step when we're using OCaml to write the smart contract, and then later we're gonna using mLIGO to export it into the LIGO language. So this is the OCaml first step. So in here we created a Dune file where we declare the library named perfect numbers with the module perfect number when we're using the preprogress ppx mligo.ppx. And we also need to create the Dune project. Dune will complain about this. And for the storage, remember we need to have two type informations. Firstly, the type of the storage, and the second, the main entry point to the project. So the logic behind the contract is we need to provide the numbers that we check if the provided numbers is greater than the current number that we store inside the smart contract. So it means that our storage is a symbol type of type int. So we can use type storage equal int. So it's the way that you define a type in the OCaml language. For the main entry point, so this main entry point of this smart contract is a functions which takes specific types at an argument, and it returns a list of operations that done by the smart contract and the state of the new storage. So the parameters and the storage, which is the parameters is a list of operations, and the storage is the update state of this storage. And this is the function main, where we define the parameters. Type is propose of type int arrow entry to main. So since our contract only have one constructor, because we only need to have like input the input numbers, so we call it propose in this type parameter. So for the function main, we have only one cases where we said main taking an actions, and the store is a pair of param, and the storage is a list of operation that we have, and the updated storage. Then we match our actions is the proposed numbers. And so now let us implement the logic of the proposed numbers. We need to check the properties that verify the function will verify the properties that the numbers that we input is equal to the sum of its divisions. And so it also should be optimized, since every single operation running on the Tesla blockchain will cost you some tests. So this is the logic of how the perfect number work. So firstly, we have a recursive functions that checking the divisions, and if it or ends, it means that in LIGO is a type NAT. So O end is only understood by the OCaml compiler that will help for the preprocessor. So this means that we divide these numbers and then we return the sum of it, which increase the numbers of the thing that we're looking for, or we just increase, then keep looping for the next numbers. And we started these perfect numbers by 0, and the input numbers started from 1 that we divided by 1. And so that for the entry point, we have only one single entry point, and we call play, where we input the numbers, and the storage, where is int, and new storage of types int and storage. So we check if the stored, like the numbers inside our storage, if it's less than the number that we provided, then we check if the perfect numbers of this is it this number that is the perfect number. Then we get the sort contract. To do that, that where we're using Tezos.get contract with error. So this is provided inside the interface of Factori to help to interact with your smart contract, and then it get the taser sort, and if not, then it said that there is no sort address. And if you the thing that we wanted is to check if this is the perfect number, then we gonna revert to the person who guessed 2000 moon days. So we call tasers dot transactions non of type unit and 2000 moon days to this sort address that we got, and we stored the reward inside a list of operations, and the numbers is the updated number in our storage. If not, then we're gonna return that it's not a perfect numbers, and or the number that we provide is smaller than the current perfect number. So here is some useful function that I explained before. Tasers get sort is we return the sort address that we call for the contract, and tasers get contract with error. It will take the address that we get from here and return the associated address. We can also, this one will return with error, or you can use another called tasers.getContract.up. This will return the option type. And for the tasers.transactions, it will make a transactions or a smart contract call by providing the parameters of the entry point. If it's a smart contract, the amount in moon days or in taser, and the target, I guess, that we wanted to transfer to. So now this is some note about mLIGO, that it needed to have a return type in every single functions call. That here you see, even it's a fair week, we also need to give the return type of each function that we have here, all the return type. If not, it's complaint about, and this will raise an error. So this is the full smart contract that we write in OCaml. Just recap again, open the mLIGO to be able to use the mLIGO library, and the type of our storage is a type int. The input entry point of our contract is a single entry point where we input the proposed with some numbers, and this is the function that checking the properties to see if the numbers is the perfect number or not. And this is the where we check, where we play with these numbers, where we input the numbers, and the storage is to the storage of our contract, and we check the number of input with the number that's stored inside the smart contract. We check that these numbers is perfect number or not. If yes, then we check, we get the sort address by using the taser.sort, and then from there we actually check, we get the contract of this sort. We will return the sort address, or we will not return it in case of error. Then we will do the operation transactions, where we do send 2000 moon days to this sort. If it's guessing the correct perfect numbers, then we store a list of operations, operation list, and update numbers in the storage. And in other cases, we can just return an error messages. Either is not the perfect numbers, or the numbers that we provided is smaller than the current numbers that we have. And the main function will call to just call play of these numbers and the initial storage of it. So now we're done. So now this is the second step from the OCaml mLigo. We're gonna use mLigo to export it to the now we have done the OCaml side, writing our smart contract and logic and everything that we needed. Now we're using mLigo to generate it into Ligo. It's the language in of smart contract from there. So we can just use two mLigo perfect numbers, and that where we able to generate it into our mLigo file, or we can actually using this adding in Dune file these rules. But before that, we need to remove the target perfect number mLigo if it's already generated before, so that it will when we call it, it's gonna run automatically when we type Dune build. So now we already have our perfect number.mLigo. So we move to our next step is to using Ligo and generated it into our Michelson smart contract. The key is to do Ligo combine contract perfect number.mLigo, and we, instead of export it into the terminal, we export it into the file named perfectnumber.tz. And if we're using the Dune that we have here to generate it, the perfect number mLigo, then it will be stored inside the build_build default function. So you just need to point at the directories that having this mLigo function, mLigo file, and generated it. Or you can add into Dune find, same thing, but remove the target perfect number.tz if you already have generated this file before. And so then it's gonna write generated the perfect number.Michelson, that where you can see or check, which is really long. This is the Michelson language. Then now we already done the all the step of the smart contract of this top level. Now we need to import this smart contract that we generated into the library Factori. To do that, we're using Factori. Remember, we import either by having the key, the address of the smart contract, or we import it by using Michelson. So we import and we deploy it. We originate this smart contract so that the Tezos blockchain registers our smart contract. So to import the Michelson file, remember now we don't have the key, the address of this contract because it's new. So we need to using Factori import Michelson because we only have the perfect number.tz. So we use Factori import Michelson's perfect number.tz, and name is the name for the interface, which is we call PN, is the short name for perfect number, and we wanted to export it into OCaml language and forces it. And this is the same if you store your perfect number in the build file underscore. You just need to point to the correct directory, and same. So this will create a new project folder inside your directory that you have been doing. This is called perfect numbers. This is from the OCaml SDK that helped to generate it. So from the perfect number is the parent, then you have the sort, and in the sort you have three folders: the libraries, OCaml scenarios, and the OCaml SDK. In the libraries, it's gonna contain the blockchain.ml, where you have all the functions to interact with your blockchain, like get sort, Tezos get sort, get Tezos transactions, and thing that you can take a look inside here, the type, and some util functions. For the OCaml SDK is where you remember we named our interface is PN is here. You can actually change into perfect number or any kind of name that you want, and this will use it to generate into two different type file. One is gold and another is OCaml interface, where it contains your interface of the smart contract that you import inside the OCaml language. And for the OCaml scenario, we have a Dune file and the scenario.ml, that where you can actually doing some scenario with your smart contract, like we're gonna see in the next step. So for this scenario, we just generated, and firstly, we can combine by using the two line here. First, make.c perfect make-c perfect number depth to build, and then to build on the dependency that this new folder, this new file needed. And then we're gonna use OCaml is the keyword to build your project. These are inside the make file. Then you can write your scenario that will come later. And then if you wanted to run, you can use make-c perfect numbers, pointed to the functions, pointed to this folder here, perfect number, and you call run scenario OCaml. This is provided in the make file. So now let us see what we can do inside this scenario. First, the function we need to deploy it, the smart contract that is called PN OCaml interface inside. So we import the PN OCaml interface here, and we call the TZ font RP is another library that provide you how to use the LWT, like this LWT let that return inside the TZ font RP. For the function main, we name the functions is perfect number KT1. We don't care about the operation hash, and we said that we wanted to deploy it. The node is blockchain. Remember blockchain here, blockchain library. We call into the Ithaca node, that where inside the blockchain it declare where this Ithaca node linked to. The name of this deployment is called perfect numbers from blockchain.alice flex data. So it's just the account that already seated inside the Ithaca node. We just said that we want Alice to be the deployer. We add some taste and some money for Alice, and then we print the address of this deployment contract. And if everything is okay, we return. So here is the explanation that Alice Flexita is the account that initially from the Flexita sandbox is already available into the Ithaca net. So in case that you wanted to use your own address or your own account, you just need to change and point into the account that you had created. And also for the Ithaca node, if you wanted to deploy into different testnet or block mainnet or anything that you could change, you need to change this here. And so for the initial storage is z.t is z1 here. Int is in Michelson is type z. So even if we remember we said type storage equal int, we generated the contract. And so we also need to remember that if the user input the correct numbers, then it's gonna give the one who created that numbers a reward. So that's why we put the amount so that we can have money to transfer. So now we already deployed the contract. So now we need to call by calling it entry point. And remember, because of our smart contract only have a single entry point, then we can actually using the function called default. So this operation hash is called default from the node, blockchain Ithaca node, from Bob. Bob is the user. And to call to this smart contract, perfect number KT1 is the one that we name here. And he gets that this perfect number is 28. And so then we're gonna print the operation hash in case that is correct. So if these numbers, there's several cases that we see in our logic on the smart contract that if it's the numbers is not greater than the current perfect number, then it's false. So here, if you remember here, if the numbers will rise smaller than the current perfect number, so here, if it's failed at the first conditions, then when you call it, it's gonna fail, and it said error, force manage operation, call entry point, kind, not area. Errors is the thing that the number that you provide is smaller than the current perfect number. And the second fail that is the number that you provide is not the perfect number. So it is the second else here, like the numbers that you provide is not the perfect number. Then it's gonna bring you this error. Then while running the scenario Factori, you may get some debug messages, but you can disable them by using like the z font.node.silent true. So here is the full final scenario where we call the open of the perfect number interface of the smart contract in OCaml. We have the LWT from the TZ font, and we write our main functions where we just set the silent on the debug method to true, which is print and deploy the smart contract, and then we're gonna using deploy it from Alice the one who deploy it. The initial state is 1, the amount input to Alice is 10,000 muntes, and then we print this originate of the smart contract out. Then we're gonna do the operation hash that we call interacting with the smart contract. Because of this is the single entry point, so we can use call default from the same node, but from pop calling this perfect number, and he gets 28. And then we're gonna check by using print out the operation hash. We're gonna do another call. Bob also get the another one is 12, and we check if the number that he proposed is correct or not. So these two we're gonna run and we're gonna see, and we can actually check the operation hash by using this Ithaca Explorer. So that I have explained everything, so let us start it to do. So firstly, up here you can do Factori, example. You're gonna use a perfect example, and we need a Dune project and Makefile. So I'm gonna just create it a new directory where I opened my thing in. I have this here opened. So I just open the terminal, I define a Dune. Okay, here you can see. Okay, Dune, what I need, Dune project. I also need Makefile, and I need a source. Okay, so we just actually copy paste everything inside. Let's just complain, doesn't matter. And Makefile. So this is the where you can see how you call run scenario, or you combine the LIGO, you combine Mikison, you call Factori, you call scenario, all these things here. So let's see inside the sort, what do we have? We need a Dune file. And we need the perfect numbers. That is the file that where we write our smart contract. So in the Dune file, remember that we don't need all these things first. We just need to define the library. So that library is named perfect numbers. It have to be exactly the name that we have is here. The module file, and we call the mligo. So we done here. Oh, sorry, this shouldn't be here. This inside Dune. Good. Then inside perfect number, we're gonna do step by step. So here we just copy all of the logic of our smart contract that we had explained before. So now we have it here, and so now we can call Dune file. So let's check. I'll see a Dune view to just view it. So now I don't have the mligo, so it means that I need to install. Remember, we need to install the mligo. So here, to install it, we're gonna do this. Open suite. This. So what it said, I just need to check. Open in. So it's gonna just tell me that I need to set correct one. I have to do it, check it again. So now we install it. because I didn't set the environment, so that's why it complained. So that I need to set the environment so that it recognize that in this terminal that I'm using the OCaml library that pointed to these versions, and then I can using opam bint add mligo inside this environment. Okay, so now we have it. What do we need? Okay, so now we just need to do view. Now it's view because it was complaining, so we viewed. And what do we have? Okay. I think you're gonna see it in underscore don't view stuff like that, but right now you don't see it because I opened not here. I should. It froze. Nice. That happened. Okay, I want it opened the full OCaml here. So it's stores in bin, for example, sort. So you're gonna see build, default, binned, under example. You're gonna see perfect number have been built. Okay, font it again. So go in here, bin, sample, then short, and we have our perfect number. Hopefully, do view again to see if you still remember. No, it's not remember. I have to switch in view. Gonna create it. So you have to let your environment knowing at which directory in the OCaml suite that you're running. There is not. If not, it's gonna complain. So we have our perfect numbers built. What we need next is using LIGO to export it inside to the here, using it to actually export it into LIGO. So to do this, to mligo perfect number, and they're gonna generate it as the perfect number.mligo here. And if we don't want, we can actually copy paste this and remove the target, and we do view again. It's gonna generate it, but the file generated will be stored inside the dot underscore build default bin and then short, and it will go further. So, and now we already have our LIGO, so we're gonna use this LIGO to generate it to the Microsoft language. To do that, we use LIGO. Let's check if we have it. No, we do not have. Now we have to install LIGO up here. Open the website, install by Dockers. Just copy. I'm using Linux. So here, running the Dockers, calling it, and we can just use the alias for convenience. So now just check LIGO. Yeah, we have it right now. So in LIGO we can use the keyword combine to combine LIGO program to application, or we can run, we can do much more stuff with icon, but now we just need to combine. Come back here, what we need, where I am. Okay, contract, and our perfect number, and I go export into perfect number.tz. Yay! So we have our Mickelson. If you want to check, you can check, but I give up. Okay, next step. Just assume that it's good. If not, we're gonna see, it's gonna complain. So now our next step, or you can also use in Dune. You copy this like in here, in Dune, and just copy this, remove this, if then remove the file, and then it's gonna generate it when you do Dune build. So now we're using Factori to import our Mickelson file. So we use Factori import, hopefully Factori, good, our import Mickelson perfect number and perfect number.tz, that dash name, just short name pn, using OCaml, and I force it. Is it correct? Yay! So what do I have here? So it said project, my Factori project created, and the thing that is print out for me that the ML file, the Dune, the Factori in TypeScript, imported, interface, build, prune, blah blah blah, and inside it had the sort, it's a library. Remember, we have library, the blockchain, Dune, on the time, the scenario, and also they have a sort. Inside the sort we have the OCaml SDK. So it's here, the perfect number here. So we have all of these actually inside this folder is generated when we using Factori import by OCaml SDK. So we have the sort folder, we have OCaml format, we have contract, we have Dune file, we have Makefile. Everything is generated that where we can call like run, scenario OCaml, we can call Maxi, deb, Maxi OCaml. Remember, we built it, the folder, we have project, OPAM, we have readme. I got there so much stuff. This is the readme that's bring it here. I gotta read it later. And inside the sort, we have the contract folder, library, OCaml scenario, OCaml SDK, TS SDK, where you wanted to use the TypeScript, but we didn't use dash TypeScript, so that we only use the OCaml language. So for the contract, we have the pn. Pn is the name that we imported here in the JSONs. We have library that contain blockchain. Inside blockchain, we have all the information that we need to interacting with the blockchains. For instance, they have the type of identity, the secret key, the public key, and they have print out this pair of key. They have the bootstrap information for the data sandbox, bootstrap 1, bootstrap 2, bootstrap 3. We have the information of Alice and Bob, where you remember we call the account. They have public key, they have public key hash, public key and secret key, Alice informations, and from there we can actually call, this is the function provided by the Factori to actually get the identity generated the identity, the information of the sandbox node, the flex. There's the Ithaca node where you are running it, and we have the main. We have get balance to check the balance of the address. We get the information of the storage. If we wanted to see what is information of the storage, we can do the transfers. Remember, we can have can do the transfers to the address, where we provide the amount, the fee, the gas, the storage limits, the counter, the node, from the address to the destination address. These question marks is optional. If you wanted to put inside, you can, but you don't have to if you don't want to. Optional informations, and that we're gonna just call the sort is from the public key. That's called from the public key, and the kind of the operation that we wanted to do is the transactions with the amount. The destination is equal to the destinations, and we don't have any parameters. And for this fee, if we input it, if not, it's gonna just keep the information, and the data method is none. Then they're gonna do signing, get checking, and printing on the information. Then if everything is okay, it's gonna return the hash. And this is another function also for the transfers, but I guess this will be a list of transfer, where you can actually having a list of destinations from transfers. And we also have another similar match transfers from the sandbox nodes, instead of all of the informations from the node to the amount form and to a list of destinations. You inject existing transfer up. Then we have call entry point. There's a lot of information. Let's create deploy contract, deploy the existing contract. Then we have this function. Remember, when we call deploy, where we do the ordinations, that where it's called create deploy this contract with the initial information. Then check parameter tag. Then this is basically inside the library. Blockchain, what's inside here? It's just all the print functions that we need for our for the thing. Util function, get and set from the batch. And so for the SDK, remember we have 5 is the interface of PN code. Let's see, we have all the information of our code that inside the is a string of our TZ mechanism is it's just code. And for the interface, we have all the entry point interface to the how to call interacting with our smart contract. So we have the storage, we have deploy, we have call default, where we actually have one single function, one single entry point when we just using this function to call. And so now in the scenario is just an empty file where you can where we can come here and we copy paste our scenario file that we explained before. So let's copy. Copy and paste easily. I don't think I have to go back again, no? So this is called PN OpenML interface, that is called from here, and from here we call deploy, and we call value. So here you're gonna see here we have the function call default is called the operation, and then we have deploy is deploy this contract. Yep. So D2 information is gonna fail because it's not the perfect numbers. But first thing first, we're gonna see what we need to combine. Now we have everything, we copy, we import. Now we have this scenario. Now we need to use maxc perfect number depth. Maxc perfect number depths. Is it? So just combine our own dependency. Okay, this done, then we use OpenML. Yep, combine it. Okay, cool. Now we run, and you're gonna see it's gonna fail, but we're gonna just max-c perfect number run scenario. Remember the Makefile here, like run scenario. It's gonna call this scenario that we combine inside the Dune file thingy. So it's gonna deploys the contract where we have in our scenario here. Firstly, we set deploy printed. We silent on the debug mode. We bring it, and now it's running the deploy. If it we call Ithaca node perfect from Alice. Initial storage is 1, and if it's correct, then you're gonna print our deployment contract, and then we're gonna call the next step. Okay, now we have this here, so it means that we've done this step. Now we're gonna check our number 28 calling this contract. It takes time. It cannot fail. Now it's print. Now you see up. Now you see that it's gonna bring the proposed 28. We come here and bring proposed 28. It bring the operation hash. Then it said error that this is the number you provide is smaller than the current perfect numbers. So then it means that there's nothing changed, but we can actually copy this contract. We're gonna use this, and we're gonna search our hash. So here you see we applied a minute ago. We created really small one here, that the number of days like 0.01 days, and it's successfully created. That's why it originated our smart contract. Then we have the Alice call this smart contract, and with the default, which is 28, the storage is 28, and it said it costs us thing it's gonna apply, but it doesn't change the storage. So let's change it. Let's change to 496, and then we have here 496, and we're gonna combine it again. I think I don't have to do that depth things. If it fails, it stops. So we don't pay for it. Come on. I think straight, then run it. Yep. If we already know our smart contract, instead of using the deploy thingy here, we can set our KT equal to the number, the smart contract call that we have. Wait again. So this is the new smart contract that we call. So each time we deploy, it's gonna generate it for new smart contract. Here. So if we wanted to keep calling and just change the code, we just remove this deploy and we put the KT1 perfect is the exact address here. Then we can just redeploy it. Okay. So this, the first one is okay. The 12 is not okay. See, the 12 it does okay. It's smaller, but the first one is okay. So to make it disappear, we don't need to run. This is just show okay of the second is not good. So we can just remove this error here. And we combine it again, and just we just check the only correct input. See, now we successfully, so we can copy and check our hash. So yes, 40 seconds ago, default, I'm gonna check the storage, 496, storage parameter we input, the storage updated right now, already updated. This is apply, the gas, the informations, transactions, who call who, the backing fee, the gas, the counter. Yep. So send. Yep. That we call this smart contract, and successfully apply. So yes, this is all. Thank you for watching.